Hi, I'm Zachary Kircher, and this is my Lidar tutorial for GHS Electrical Engineering 2025, taught by Coach L and John Barry. In this tutorial, I'll be using the Garmin Light V3 HP Lidar module. This is a simple lidar module which measures distance by sending out a laser, and then once it bounces back and receives it, based on the amount of time it takes to come back, it converts that into distance in centimeters. The way I wired it is called an I2C, which is a two-wire serial communication protocol used to connect multiple integrated circuits on a single bus. It uses two wires, SDA or serial data, and SCL serial clock to facilitate communication between a master device and one or more input devices. This allows for simpler wiring and less usage of pins on the microcontroller. The connection requires a 680 microfarad capacitor, which are components that stores electricity and then discharges it back into the circuit when there is a drop in voltage. They are made with conductive metal plates separated by an insulating material called a dielectric. It also requires two 4.7 kilo-ohm resistors, which are used to slow the flow of electrons in the circuit, reducing the current. Now, it recommends between 1 to 10 kilo-ohms, but 4.7 is the ideal amount of resistance. In addition, I will also be using an LCD screen, which is a 2-row with 16 columns forming a 16 by 2 display to display the distance. And with that, I will also need two 220 ohm resistors for the display and LED backboard power. To start off, I'll show you the working circuit. As you can see, the circuit requires a lot of wires due to the many connections needed for the LCD and lidar, so I'll try my best to point out where the connections actually lead. I'll begin by explaining the connections of the circuit, and there will be a video in the top right corner of the actual circuit running. To start off, we have the 5-volt connections right here, which you can see come right over here and go to the capacitor, as well as over here to the resistors, which will lead to two of the connections. Here we have a ground wire right here running to the ground rail, so I can supply ground throughout the entire circuit. We also have a ground wire running to the other side of the capacitor right here, this white wire, which connects back over here to the ground right there, just moved. We have the lidar, which these two black wires connect it to the SDL and SCL, which I explained earlier, which allows for the I2C connection rather than a PWM connection, because you need the PWM slots for the lidar. We also have these connected resistors, for the power for the LCD display and the LED backlights, which you can see right there. We have here's the grounds for the LCD, which are here and here, and then these five wires connect to the digital inputs, digital outputs right here. So essentially, there's the D7 to digital 2, pin 2, D6 to digital pin 6, D5 to digital pin 4, and D4 to digital pin 5. The state of this 7 to 5 data pins, high or low, are the bits that you are writing to a register. When you write the values you're reading, the RS pin is connected to the digital pin 12, which controls where the LCD's memory you're writing data to. You can select either the data register, which holds what goes on the screen, or an instruction register, which is where the LCD controller looks for instructions on what to do next. The read-write pin is connected to ground, which is down here, this orange wire, and it is selects reading or writing mode. Then there is an enable pin connected to digital pin 11, which is right here. And this enables writing to the register. And then there is VDD, which is connected to the ground, and VO, which is connected to the output of a potentiometer normally. However, in this tutorial I just set it's right there. And then finally we have the ground and power to the LED backlight, which are these two right here, this resistor. Next we will zoom into the actual working circuit, and as you can see here, we have it displaying in feet on the bottom, and it's a little glitchy because it's pretty far away right now. It's measuring to my ceiling. And we have it in centimeters, which is about 150 centimeters. So my ceiling's 150 centimeters away. If we were to put, say, my hand in the way of the beam, you can now see that it's changed to a much closer amount. That's 0. And then it increases back, and you can see that little bar at the top moves with my hand. And that's the working circuit. Next, I'll be looking at the schematic symbol for this tutorial. As you can see, we have the different schematic symbols I explained earlier. We had the Lidar. We have the two 4.7 kilo ohm resistors, as well as the two 220 ohm resistors. We have the 680 microfarad capacitor. We have the Arduino Uno, and we have the LCD. The LCD is connected to ground, right here, power, to that 5 volt, and here are the different digital connections. DB4 to DB5, D5 to D4, D6 to D3, and D7 to D2. And then these two are connected to the power coming from the capacitor. These two are connected to the resistors, which connect back to the SDL and SCL, SDA and SCL connections on the board, and that is the schematic. Finally, we will be looking at the code for this tutorial. Here is this is some description of the Lidar code I got off the Garmin website. Here we have the different required libraries. This one is for the LCD. These three are for the Lidar module. This distance variable will be changed when it's updated later in the code, and it is for the distance that we'll be printing to the screen. This defines the Lidar module. This defines the type of connection we're using, which is that I2C. This monitor pin defines the pin that we will be using to send data to the serial monitor, or in this case to our computer. This defines all the ports for the LED. This is all to create a custom character for the LCD screen, which works by lighting up pixels in one of the boxes in the columns. Certain pixels are lit up by changing the 1s and 0s here. This is used for the placement of the graph line. I'll explain in further detail once we get to it. Here in void setup, we have the serial begin, and this is the required rate of communication for the Lidar. This begins the communication between our Arduino and the Lidar, and sets the I2C frequency to 400 kilohertz. Next, we configure it. Also set the pin modes to input, output, and set the trigger pin to high. Next, we will start the LCD, clear it, and also create that custom character and label it as 0. Down here in the void loop, we have the variable distance, which will stay the same distance variable I mentioned previously, and also the new distance, which will be used to constantly check if the distance has changed and print that. This file 1 makes sure all the stuff below is constantly happening. So new distance will equal the distance continuous, and this is for something below that checks for the new distance. And if there is a new distance, do this. Begin by serial printing the distance. Set the cursor to 0, 1, which is the first row, first column, and write Lidar centimeter measured. And if the distance is, so these next if statements are all the same, so I'm only going to explain one to avoid tedious explanations. So if the distance is less than 10, first set x to 0, and then LCD set cursor x, 0, which x is used to set which column it is in the first row. And then it will write the custom character 0, which we defined earlier, delay of 100, and clear it, and repeat that process. And then here you can see it keeps going and going until it gets to about 100, if it's greater than 150, and that's the end of the bar. Down here is the continuous distance measurement function from the Garmin website. It essentially checks if there is a new distance and returns that value so that we can use it back up here. And that's the code. And with that, that is the end of my Lidar tutorial for GHS Electrical Engineering 2025.